So hello everyone, this is Susinder here. Thank you Asif sir for the introduction and the opportunity to present at support vectors. So today we're going to discuss this paper, Cauchy activation function and XNet. This paper was submitted in arXiv in September of 2024, not long ago. So pretty recent paper. It presents a very interesting idea, and let's just walk through the abstract first, and then I will break it down and simplify what is the essence of the paper. So let's just read the abstract, and then I will explain. So the abstract says we have developed a novel activation function named the Cauchy activation function. This function is derived from the Cauchy integral theorem in complex analysis and is specifically tailored for problems requiring high precision. This innovation has led to the creation of a new class of neural networks, which we call XNet. We will demonstrate that XNet is particularly effective for high-dimensional challenges such as image classification and solving partial differential equations. Our evaluations show that XNet significantly outperforms established benchmarks like MNIST and CPAR-10 in computer vision and offers substantial advantages over physics-informed neural networks in both low-dimensional and high-dimensional partial differential equation scenarios. Okay, so there are quite some terms listed here for those who are new. First of all, there is this term that we see called activation function. So what is this activation function? I will explain that for those who are new. I hope some of you might recall this Cauchy integral theorem. Maybe several years back for some of you. Sometime in high school, or you might have encountered in engineering if you have done a course on engineering. Integral calculus, right? Any calculus courses if you had taken, you might have come across this Cauchy integral theorem, which comes in very handy to calculate certain integrals, especially on the complex plane. And you also see this term called neural networks. Hope that is not alien to some of you. The whole world is talking about neural networks. So hopefully the term neural networks is not new to you, but I will introduce some of the basics in this. So first of all, there is some background that we need to know before we get into this Cauchy activation function. So the neural networks, as you know, it all is based on this theorem called approximate universality theorem. Okay, and what that sorry, people asking to zoom it a little bit more. Okay, yeah. So what the approximate universality theorem says is, let's say you have a function, right? Let's say your input is x, and you have some function of x. That you want to approximate. Okay, so we don't know exactly what that function x is. Usually what we are given is, we are given several data points, several pairs of x1 and f of x, x1, like that, and x2, f of x2, like that. You are given several data points, and then we try to fit a function that kind of best approximates this function here. So what we try to do is, we try to create a neural network, what is called a neural network, which has some parameters, okay? And we try to tweak these parameters in such a way that the output of this neural network closely approximates this function here. That's essentially what we are trying to do in the neural network paradigm, right? So in that context, there is a popular class of neural networks, which probably was the first class of neural networks that came. It's called multi-layer perceptron, or MLP. Some people call it as feed-forward networks, right? And this is directly comes from the approximate universality theorem. Okay. Now, what that multi-layer perceptron or that class of neural network looks like is, let's say our X is n dimensional, okay, and x1 to xn are those n coordinates, right, of that n dimensional function, right? So this comes as the input x1 to xn, and then what we do is we just do a weighted sum of all these inputs, okay, n dimensionals. We just add a weighted sum, and the weights are w1, w2, and so on up to wn, okay. So we do a weighted sum. So in terms of equation, that will be like summation I is equal to 1 to n wi xi, right? So that is your weighted sum output. Then what we do is we add a bias term. So that is your B term that you see here, and that gets added. So this is basically nothing but a linear transform, right? So it's basically a weighted sum of the all the n-dimensional, and then you're adding a bias term. So this is a linear function. Now, what they do is after taking this, they apply what is called an activation function. Okay, and that is what I'm calling here as this G. This G is the activation function, and this is a non-linear function. Okay, so G is some non-linear function, and why do we need this G is basically, finally we are trying to approximate this F, and this F, if it is linear, we don't need the G. If you are trying to approximate a linear function, we don't need the G. Okay, so this linear weights itself is probably good enough to approximate it. But most problems that where neural networks gets used is in the cases where F is nonlinear. So if you want to approximate a nonlinear function F, what the approximate universality theorem says is you need this activation function or a nonlinear activation function G. Okay. Now, this is one neuron. This is the output of one neuron. What I have shown here is the output of one neuron. Okay. What the approximate universality theorem says is you need multiple neurons like this. So let's put another neuron like this. I've just shown here, this is what happens in one neuron. But you need multiple neurons like this. And this is what we call as the hidden layer. Okay, so this is what we call as a hidden layer, and each of these neurons is basically doing a weighted sum, and these weights will be different for each of the neurons. Like, we had one set of W1 to Wn, that's for the first neuron. You'll have a different set of weights and a different bias term for the second neuron, and so on. But we'll have the same activation function G. Okay, so the activation function is same for all the neurons, and it is a fixed function. Okay. And what this approximate universality theorem says is, so this is your hidden layer where you have, let's say, the number of neurons in the hidden layer is, let's say, L1. Okay, so this is layer 1's output. You have L1 neurons, so you get, L1 dimensional output. Now, to get the final output, we have let's say a single neuron, right? And then this single neuron will take a weighted sum of all these L1 neurons output and then apply activation function G to it, okay? And then that will be your final output, okay? And then what we do back propagation, right? So we do the training, and in the training process, what we do is we take, we assume we have a labeled data set, so which means we have lot of data points of x and f of x, and then we do the back propagation, and that will basically give you a set of values for these w1 to wn and the bias terms, right? in such a way that the final output of this multi-layer perceptron matches or closely approximates the function f. Okay. Now, what the approximate universality theorem is guaranteeing you is that it says for some choice of L1, that is, if you have sufficiently large number of neurons in your hidden layer, it can pretty much approximate any continuous function. So that is the beauty of the approximate universality theorem. Okay. Now, this is all, probably 20 years old now, or probably much more than that. But I'll just give a basic intro for people who are new. Now, the key point I want to highlight here is this function g, right? This function g, which is what we are calling activation function. This is a fixed function. So it is not one of the parameters that is trained. Okay, it is a fixed function. What is being trained, or what are the parameters that we are actually trying to find during the back propagation, is this wi and the b. That is what we are trying to find. Okay. Now, what I have shown here is a simple, one hidden layer. Now you can build up on this idea, and then you can have multiple hidden layers. Like you can build another set of, let's say second layer you have L2, and then you can have a third layer. You can have let's say L3 neurons, and so on. You can add multiple layers, and finally you can bring a single neuron output. And if you do that, you are said to be doing deep learning. So basically you have a deep network, which means you have many layers. Okay, so that's about the background. Right now, what should this G be? Right, so this has been a topic of research for many years. People have tried various types of activation functions, and I will show you some of them. And if you just go and Google activation functions, you will find like probably 50 or more different activation functions. Some of the popular ones are ReLU is an activation function. It's a popular one. Sigmoid is another popular one, right? Like that, there are many popular one, and people have tried to see for what type of activations functions we get good accuracy in approximation, right? What gives us the good accuracy in approximation? What gives us faster training? What can expedite the training process, right? So like that, people have researched, and there has not been I would say universally accepted, like, okay, this activation function is going to perform well in all kinds of problems, right? So the real answer is the best function G is really going to depend on your F, meaning depending on the problem, you will have to pick the right activation function. So it's hard to say one activation function will kind of be the best for all types of problems. But anyway, if you add enough number of layers and neurons, you can still fit and it will still, the approximate universality theorem will still guarantee your output, right? But it may not be the efficient way of doing it. Okay, so this paper, now let's come back to this paper. What this paper is trying to say is it's proposing a new activation function. Okay, and this activation function is coming from the Cauchy integral theorem. Okay, so let's just look at some of the the ReLU function. So this is the ReLU function that I talked about. This is pretty popularly used, and then this is the sigmoid function. This is how it looks. Okay, and the Cauchy activation function that this paper is proposing is a learnable activation function. Okay, so that looks like this. Okay, so it has three parameters: lambda1, lambda2, and d. Okay, and x is the input. Okay, and so it says lambda1 x by x squared plus d squared plus lambda2 by x squared plus d squared. Okay, So what is interesting here is this is a learnable activation function. So unlike the MLP case where we had fixed activation functions, here what we are doing is, or this paper is proposing, to make this activation function itself learnable, and it is parameterizing it with just 3 parameters. Okay, and and they go on to show that it gives good results in varied types of scenarios. Okay, so that's essentially the crux of the problem. Now, if you see this activation function, it comprises of 2 terms. There is an x by x squared plus d squared term, and there is a 1 by x squared plus d squared term. Okay, so and they've just plotted these 2 terms, right? And basically the final output is a weighted sum of these 2. So lambda 1 and lambda 2 are those weights, right? And you can see the term 1, which is the x by x squared plus d squared, it looks something like this, right? The orange curve. And then the blue, sorry, the x by x squared plus d squared is the blue curve, and the orange curve is the 1 by x squared plus d squared. Now, why do we have this d squared term there is, if you don't have that d squared term, then you could end up with, when x is 0, then it just, the output blows up to infinity, right? So to avoid that, you have that d squared term. So it kind of adjusts, like you can think of the width of this lobe, like how big that lobe is, it kind of adjusts. That d parameter will kind of adjust it. So you can see these are basically 2 different shapes, and the final activation function is going to be a weighted sum of these 2 functions. Okay, so 3 parameters, lambda 1, lambda 2, and then d. These are the 3 parameters that are learned. Now, this is some mathematical background as to how they arrive at this. Little bit of background on the Cauchy integral theorem, and so basically there is this Cauchy approximation theorem, okay, and which says basically an n-dimensional function can be approximated by this term, basically summation k is equal to 1 to m. Some lambda k's are the weights divided by basically epsilon 1 power k minus z1, lot of terms like this. Okay, so this is what the Cauchy approximation theorem says. From that theorem, what they do is, or this paper does is, simplify, take the special case of 1 dimension. So go down to 1 dimension. By the way, this is for in the complex domain. So all your epsilon are all complex numbers here, and the lambdas are also complex numbers. So they take the n is equal to 1 special case of n is equal to 1, in which case it kind of simplifies to this, and then further simplify it to the real case. Okay, so you want only real valued function. When simplified further to the real case, you end up with this function. Okay, so after some simplification and then taking out just the real parts, you will basically end up with this function. Okay, now what they're saying is this function can do a good approximation of any continuous function, 1-dimensional function. Okay, so it can approximate a 1-dimensional function pretty well. Okay, so for some choice of lambda 1, lambda 2, and d. Now, what do you do for n dimensions, right? So n dimensions, what they're basically saying is, in the MLP, right? In the MLP, just replace that g, that activation function g, with this Cauchy activation function. So, and this is what the general approximation theorem states. Basically, they're saying weighted sum. When you want to extend this idea to n dimension, you do the weighted sum, and then have these Cauchy activation function as the g. You will basically get your output. And this type of neural network, they are calling it as XNet. Okay, so XNet is simply, right, if you just read the last line, right, compared to popular neural networks, it appears that only the activation function needs to be changed. Okay, so that's basically the change that they're doing. Now they show a lot of examples where they apply this, right? So pretty much simple, right? This is like a very quick drop-in replacement, right? In an existing MLP, all you have to do is instead of ReLU or sigmoid or like GELU or whatever activation function you are using, just replace that with this learnable Cauchy activation function, and they're applying it to few popular problems. As you know, MNIST is one of the very popular, or it's like the hello world of machine learning. Okay, today it's like the hello world. Probably there are bigger problems which have become hello world now, but MNIST is like a very trivial problem today. So it's basically a handwritten digit recognition problem. Okay, so you have digits 0 to 9 which are handwritten, and they've taken images, and those images are captured in 28 by 28 grayscale image, and you basically have it's a image classification problem. Okay, and this is a well known, and it's pretty much thrashed problem right now, right? Uh, with the MLP itself, it is already solved, and then there is convolutional neural networks, and there's vision transformers, and all kinds of advancements have happened, right? But we just going to go and then try to replace the activation function with the Cauchy, right? So they did that, and what they are showing here with the MLP, if you use the ReLU activation function, right? So this is the, sorry, one second. I'm just trying to zoom this. Yes, yeah. So if you see here, the training loss for the ReLU, that's the blue curve, right? So that evolves like this over time. I mean, over the number of epochs, right? So that's the light blue and the light pink are the training loss and validation loss for ReLU. Now, when you just change it to Cauchy, you can see the training is much faster. Okay, and not only that, the final loss is also a little bit smaller, right? Similarly, that reflects in the accuracy also. You can see in the accuracy also, the light blue and light pink are for the ReLU, and the dark red and the dark blue are for the Cauchy, and you can see the accuracy is also better. So the MNIST, they show that they are giving better results. Similarly, they apply the same idea to the CIFAR 10 dataset. There also, here they're using a CNN, which is a convolutional neural network. And in the convolutional neural network also, you have this activation function. There they replace the ReLU again with Cauchy, and then they show better results. They also apply it in the ResNet architecture, right? There also they show that it is doing a better job, right? You get better accuracy. So here you can see the results. ReLU is 78.9% accuracy, and Cauchy is like better than that, right? So basically, in all the neural networks that we know, you can just do this drop-in replacement, and you can get a slight boost to your accuracy, and you can get a much faster convergence also. They also tried applying it to partial differential equation, trying to find the solution of partial differential equations, right? So for this, they used a physics-informed neural network, right? And
can I ask one question?
Yes.
So, but there are 3 additional parameters for every neuron, right? So doesn't it take longer than to train?
Surprisingly, it doesn't. It actually quite the opposite. It trains faster, actually. So yes, there are 3 more parameters, but per neuron, but that's not a lot of parameter addition. But it's interesting, that it actually trains faster when you have these activation functions as learnable. I think, I don't know exactly why the dynamics are better. I don't have an explanation, nor do the authors actually give an explanation. But intuitively, uh, it feels like, when you're in the early stages of the learning, right, you have no idea what the function is. And when you have already made up your mind, okay, this is my activation function. I'm going with ReLU, right? And you can see this ReLU activation function, right? The gradient is 0 for negative numbers, right? And that's where, they come up with different activation functions. But what I'm trying to say is the optimal activation function is probably, it's too early to make a judgment in the early part of the training. So leaving it a little bit fluid uh, probably, helps in that way. So in my observations also, which I will show today, you can see consistently, I've tried in multiple neural networks, it trains much faster because these activation functions are fluid and nowhere the gradient is zero for the Cauchy activation function, right? If you see, I mean, of course, it becomes zero when for large x, right? Either negative large x or positive large x, it kind of decays down to zero. But for much of the values around zero, the gradient is not zero. So that's like a nice property, which probably is helping in one way. But I think keeping it fluid helps. So anyway,
Thank you.
uh, proceeding to the physics informed neural networks also, they try to find solutions of the partial differential equation, and there also by just replacing sigmoid with Cauchy, they show better results. And of course, they extend it to higher dimensional partial differential equations. Basically, the conclusion is basically the same. Okay. Now, following up on this paper, right, there has been one other paper which came just a month later than this. So, which is this paper? Okay, so this is, yeah, this is just presenting simulation results. No new ideas presented here as far as I could read. But they're just doing a comparison against a different class of neural networks, which also has gained quite a bit of what do you say interest in the community, which is the Kolmogorov-Arnold networks. And what they show here is in their test results that interestingly, the XNet based on the Cauchy activation function outperforms the Kolmogorov-Arnold networks. And I think there was a separate talk on Kolmogorov-Arnold networks. I mean, I don't think I can do justice in a few minutes. But basically, it's a very different idea, of neural networks, where if you see in the context of the MLP that I explained, if you think about it high level, right, you have linear functions which are matrices and they are learned, and then you have activation function or nonlinear function which is fixed, right? So this is your MLP, multi-layer perceptron. What the Kolmogorov-Arnold network says is you have basically learnable activation functions, and then you get rid of the matrix. There's no matrix. And then the output of all these activation functions, you just add up. Just add up. That's it. So basically, you have a fixed addition, and then you have a learnable activation function. So it's like the other extreme where, all the learning happens only on the activation function. And then the operation that you do is always only an addition, not even weighted addition. It is always just addition. So all the learning has moved to the activation function. So that's the Kolmogorov-Arnold network approach, and that's a completely different way of doing things. What this paper is showing is MLP with just replacing the activation function with Cauchy, which is what they're calling as XNet, it performs better than the CAN. And they show it in the physics informed neural network context. And they show this in simple function approximation also. Let's say, simple functions like step function. So they show three functions that they show here. One is a step function. Let's say you want to approximate just a step function and then compare how the CAN does it, how the XNet does it. and then take this function, just a two-dimensional function, e power sine of pi x plus y squared, and then compare both, and then f of x comma y is xy. And then they also look at some high dimensional function examples, and in all cases consistently the XNet outperforms the CAN. Okay, and we can actually see the results here. So here they are showing, let me zoom in. Yes, I have a problem with zoom. Yes, so if you see here, let me zoom in further. You see here, this is the original data and the prediction. Pretty much perfectly matches. It has perfectly approximated, and this was approximated with 64 basis functions. So you can assume there are, 64 Cauchy activation function outputs. They are all, weighted sum of them. Okay, and then you are able to perfectly approximate a step function, which is like, the what is it? Pretty. It's actually a discontinuous function, right? And it still does a very good job. And the same thing if you try to do with CAN, right? You can see something like this Gibbs phenomenon happens. People who are aware of Fourier series, right, will know that if you try to approximate square wave with a lot of sine waves, you cannot actually approximate. You need infinite sine waves. Even then, you will see these ripples happening, and you can see those ripples here. And this is shown for like different types of cans also. There in cans also there is a lot of flavors. There's beast line cans, there is Chebyshev polynomial based cans, there is wavelet based cans. So they compare against all those, and then show all cases the XNets perform much better. Okay. So that's pretty much this paper. You can go through it, and they also apply it to LSTM. LSTMs is sequence model problems, right? Where input goes a sequence, output also is a sequence, and in the LSTM they go and replace the activation function with the Cauchy, and there also they show that, which is what they are calling as XLSTM, because the Cauchy is added there, and they show that the XLSTM performs better favorably compared to the CANs. So that's pretty much this paper. Now I want to just walk you through a little bit of code, okay, for those who are interested in the code, and I also wanted to kind of share my experience using lightning.ai. And I really like the lightning.ai, and I would really recommend it for newcomers into this field to try out lightning.ai. You can really save a lot of time, and especially if you don't have a system at home. See, to do all this machine learning, right, you need a system, you need a GPU, you need an environment, right? And it takes quite a bit of time to kind of set up all these things. It's been made much simpler today, but the nice thing about lightning.ai, it all runs in the cloud. And by the way, I'm running a free account, okay? I'm not paying anything. And they also give a GPU for free, and which you might say, oh, this is what Google Colab used to do. But there's a difference. In Google Colab, there's no persistence, okay? So they give you for a time, for a limited amount of time, and as long as you want to use it, you can keep using it. But let's say you take a pause and then you go talk to somebody for 15 minutes and come back, the whole thing is gone. Then you have to start from the scratch and load up everything once again. The environment, all the libraries that you installed, everything has to be redone. That's not the case with lightning.ai. So it has a persistent environment. So I can just shut down this browser right now. Tomorrow I can open up. It will exactly wake up exactly at the same point where I left it, and I can continue. Which is, I think it's a great feature, and as I said, for newcomers, it's going to be great. So I tried like very simple problems. Okay. So this is like, you can even say these are dummy problems. Why you are even showing it, right? But just for the fun, right? I like to play with dummy problems because it gives a good, understanding. If you take very complex problems, right, where you don't know what to expect, it's kind of difficult to, get that full, understanding. So what I'm doing here is, so this is just importing all the libraries, okay? And here is the Cauchy activation function. So all you have to do is create a class like this, okay? Class Cauchy activation function, and you have to just subclass this nn.module, okay? And in the initialization, you just have to define 3 parameters, okay? So there's lambda1, lambda2, and then there's a d parameter, and these are all one-dimensional parameters only, okay? So, and initial value, I'm putting a value of 1.0, okay, for lambda1, lambda2, and d, okay, and then you have to define a forward method, okay. So this is the forward method inside it, and which is supposed to give the output of that activation function. I first compute this term x squared plus d squared, which is what I'm doing here, x squared plus d squared, and then what I'm returning is basically basically the lambda times x by x squared plus d squared, and then a lambda 2 times 1 by x squared plus d squared. So this is the Cauchy activation function implementation. Then I don't know what's happening here. I don't know what happened. It's reloading. Okay, so now what I'm doing is the dummy problem I want to do is I want to try and approximate this function 1 by x squared plus 9. Very simple problem, right? We're just going to approximate this function 1 by x squared plus 9. So I'm creating my own data set, okay? So for that, you just have to subclass this data set, and then you have to define a get item underscore get item method, which will just return one sample, right? One data point, okay? And all that gives is, okay, it returns x and 1 by x squared plus 9, which is what it gets returned. Now what I'm feeding it is, I'm taking all the numbers from minus 100 to plus 100 with the interval of 0.001, right? And then creating my data set instance, okay? And then I create a training data, right? And from that, then I'm defining my model as the Cauchy activation function. So I'm creating an instance of that Cauchy activation class here. I'm using the mean squared error as the loss function. As an optimizer, I'm using the Adam optimizer. And then here is my training loop, okay? So what I'm going to show here is, so we initialize with lambda 1, lambda 2, and d as 1, 1, 1, right? And then after the training, and I'm just going to run it for 10 epochs, okay? So at the end of the training, we want this to approximate 1 by x squared plus 9, right? So if you go back to the function, right, here, so which means we need lambda 1 to be 0, lambda 2 to be 1, right? And then the d squared should be 9. So we want d to be 3. So which is what the final solution that, we don't need a neural network for this. We can just solve it by hand. But I intentionally picked this example so that you know what the expected answer is, and then you can compare and see whether the neural network really learns, right? So let's just run this and then see that. So it's training right now. Before training, the values are lambda 1, 1, lambda 2, 1, and d is 1, right? So it's running the training now. And we can see the loss is kind of coming down. And at every epoch, end of every epoch, I'm printing the values of lambda 1, lambda 2, and d. And you can see, at the end of the training, by the time it reaches 10 epochs, right? You have lambda 1 pretty much 0, because e to the power minus 10, that's pretty much close to 0. Lambda 2 is 1, and d is 3. So it's perfect, it has hit it. And we can see this is the 1 by x squared plus 9 function, right? So this is the second term in that Cauchy activation function, right? Now we can just change this to become, x by x squared plus 9, and then we can rerun this. And now you see, you get the first term, which looks like this, right? Now, this is just a dummy example, okay? Now let's take some real example. Let's try to reproduce the MNIST. You remember in that paper, we saw the MNIST, we had a table comparing the results. So I'm going to reproduce that exact curve for you, right? So let's just walk through this code and then we'll run it, right? So this is just imports, same class, this is the same, no changes here, okay? And then I'm defining a neural network here, okay? Now remember, the input here is image, okay? So input is an image. The size of that image is 28 by 28, okay? 28 by 28, it's a grayscale image in the MNIST dataset. So first thing what we have to do is, vectorize it. So we take 28 by 28 and make it a single dimension. So 28 times 28, it becomes 784, okay? And then I'm going to have a simple, MLP, okay? So the first layer is going to take 784, which comes as input, and then transform it to 128 neurons, okay? So first layer is going to have 128 neurons. Then I have one hidden layer, which transforms these 128 layers to another 128 layers, okay? And then final output layer, it takes the 128 neurons and then transforms it to 10 neurons, okay? Why 10 neurons? Because we have to recognize the digits 0 to 9. So totally 10 classes are there. So that is why the final output layer is 10. Then I have to define a forward method. So the forward method is pretty simple. So first step, we have to vectorize it. So which is what this first statement is doing. It's converting into one dimension, two-dimensional image to one-dimensional vector. Then we are applying the first input layer. Then we have the activation function 1, which is actually coming from outside. So we can, when I create this neural network, we can pass either ReLU here, or we can pass an instance of Cauchy activation function, okay? So, so activation function, then we have a hidden layer, then again activation function, then output layer, okay? So then finally you return the output. Now this is a training loop. I guess this is very standard. I'm going to skip this. Okay, but basically the loss function is probably worth mentioning. So the loss function I am using here is the so the data is coming from MNIST. Okay, so this is a standard data set. The loss function is the cross entropy loss function I'm using. Optimizer is Adam optimizer. Now here what I'm doing is I am defining two neural networks. Okay, one using the ReLU activation function, which is the ReLU model, right? So here you can see the activation function I'm passing is the ReLU function, and then I'm creating another model XNet, which is the same neural network class, right? Instantiated with Cauchy activation function. So I've created two Cauchy activation functions. So basically you have two learnable activation functions there, right? And then we're going to train both ReLU model and then the XNet model, and then we're going to compare the results. So before we run the training, we will plot the activation function. So we'll see how the activation function was, before the training, and then at the end of the training, we will again plot how the activation function looks, and we'll also show how the training loss progress with time, how the training accuracy progress with time. So let's just run this code. So this. So right now it's running in CPU. Okay, so the device here is CPU. Okay, but I just want to tell you, in case you want to switch to GPU, what you have to do is, you see this, on the right hand side dock, you see the symbol CPU. You just click it, and then you can say switch to GPU. So if you say switch to GPU, it'll run, faster. Of course, it's a free cone, so they don't give you A100 or H100. They'll give you one of the low-end GPUs. But I think they have a $50 plan, $50 per month plan, which will give you a little bit higher end, GPUs, right? But this problem is small enough. We don't really need the GPU. But just for information, I wanted to tell you. Okay, so this is how the activation function looks before training. Now we're going to do the training. So it's running the training now. So we can see, how this progresses. At the end of 10 epochs, we can compare how ReLU performed, and then the same 10 epochs, we can see how the XNet performs. Okay, so at the end of 10 epochs, ReLU got training loss of 0.12 and accuracy of 96.26%. Now let's see, XNet is training right now, and we can see in epoch 4 itself, the XNet has achieved 96, and 5 it's actually beaten the ReLU model. Yeah, so it went to like 99.17. This is just 10 epochs. We can run further and then see, but beyond that, you don't see a lot of improvements. So here is how the training loss, evolve with time, the ReLU and the Cauchy. And if you compare against the original author's paper, you'll pretty much see the exact graphs there. So we have basically, reproduced those exact same graphs. And at the end of all this training, we can plot and then see what is the final values of lambda 1, lambda 2, and d that we got. So this is how the final activation function, that the learned activation function looks like. Okay, and these are the parameters. Yeah, so hopefully, that gives you a good idea of the potential benefits of this Cauchy activation function. I have personally tried this in also state space models, and I also tried it in transformer based models. You remember in transformer also, there is a feed forward block inside the transformer. So in that, we can use this Cauchy activation function. And what I observed is that the learning is much faster. So it trains much faster. It reaches the optimal loss much faster compared to the fixed activation function case. And I observed it even in the state space models. Like I've tried S4 model, the S4 state space model, which is also I saw the similar results. So yeah, so that's it. Any questions, comments?
Yeah,
Yes.
it's great. Yeah, so thank you. It's great. One thing in my mind is, it looks like everything is positive, right? Is there any downside, or is there any limit of this Cauchy function compared to other activation function, or where this cannot be making sense? For example, if the gradient, if there is a vanishing gradient happens, right? Is this behaves similarly or same or better? So, what is the
I have
downside? Is there any downside of this?
I'm not aware of any big downside. If at all you want to say a negative, I would say, okay, there are 3 more parameters added per neuron, which I think in the large scheme of things, it's negligible actually. So I see it overall, my personal opinions, it's overall, it's a nice addition with good improvements worthy of trying. I think you should try it in all the problems that you have used. I think it generally helps. So the vanishing gradient, in fact, there also I think it will do better. Why I say is I have tried training transformers with like 10 layers. So I've gone deep transformers, 1 million plus parameters I have trained. So even then, I did not observe any problem. And by the way, all this vanishing gradients, right? You have this residual network concepts, right? So you have this skip connections there. So that that's how people have been solving vanishing gradients, the skip connections, and then of course attention blocks also help with it. So yeah, I have not so far observed any negative per se of this.
Oh, okay. Right. Thank you.
One question, this function that you're showing finally, it is one of those trained activation functions, right? There will be one for each of the neurons, no? Isn't it like
Correct,
that?
correct. Yes, yes. So I have plotted, I think this is, since it did 2 plots, so this is probably plotting the second activation function. But you can see the parameters. The
Right.
parameters are not very,
Oh, almost
very
same.
different. Yeah, they're almost same in this case. This is by the way a simple problem. Okay, so if you need to take much more complex problems, then it might you will see, definitely you will see different values and different layers.
So within a layer also, for every neuron it can be different, right? Or it
Yes.
has to be same?
No, you can have it to be different for every neuron. Yes. Yeah. Yes.
Yes, so you said that there was an activation function and there's parameters for the activation function for every single neuron, right? So say you have a layer that has 128 outputs. You're saying that there's one parameter, like set of parameters for each of those, right?
Yeah, so you see, imagine it's like the bias term. In the MLP you have a bias term, right? So the bias term is not a big, overhead.
The issue I have is if you go to your implementation, does that do that? Because only if you want to define one for every single parameter, does there have to be a vector of lambdas and a vector of p's? Or d's or whatever? Because in your case, you're just doing one. So what's going on in this one is that it's multiplying the entire vector from the linear layer.
Correct, correct. So in my case, my implementation, I have done like that. So it is applying it to that whole vector. Yes.
But
so
it's
the first
significantly faster and not as expressive as the one described in the paper would be, right?
Yeah, you can. I think you can do what you're saying, but I find this itself gives pretty good results. I haven't tried making it different for every neuron, which may be more expressive, as you say, but it does come with more cost, right?
But is that what the paper wants to do, or is that do they like leave it up to you whether you want it?
I think they didn't explicitly mention that. Because even in the MNIST problem, right, I even tried to have one activation function for all neurons, but then keep it learnable. What I found was even that was giving little bit benefit. So I could see the benefits even in that case. Yeah. 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 Thanks, man.
Hi, Susinder. This is Shirang. We also lost touch some time back.
Yeah, nice to
nice to see you. Yeah, pretty interesting idea that you picked up. So the question I have is open to everybody actually. If you look at that shape of the Cauchy that's come out.
Yes.
What is the intuition? What is going on? I mean, is it like to me, it has, I'm trying to visually understand this and what effect it must be having to the function. Is it has bends in both direction. It has raises and lowers in both direction. So I'm trying to visually compare different activation functions and what actual effect does it have. Each, you plotted one, and at each neuron, their rise and humps and could be a little different, right?
Mhm.
The slopes and all of these are going to be different. So I'm trying to understand it. Let's just say that they all kind of this family, like one hump, the other hump in the other direction. So I'm just trying to understand what effect is it having for the. It's almost like a B-spline function approximating between poles, between points, so that the curve gets pulled down, or I'm trying to get an intuition as to exactly what is going on there. And why is Cauchy ends up becoming better because of its forces in different directions, actually.
So one thing you can see is the gradients, right? So there are these two terms, right? X by x squared plus d squared and 1 by x squared plus d squared. Both these terms have pretty much the slope becomes zero, right? Close to zero for large values of either positive large values or negative large values. The slope becomes zero. But if you see values around zero, it has a nice, it's a non-zero slope, and it's like a smooth, even so gradient also is nice and smooth, and it's the gradient, the slope is probably maximum around zero. So you have this, more the slope, that means essentially more the learning, right? The gradient is more, means more is going to be the learning. So
yeah.
So basically, it has good learning properties for values around zero, and it doesn't learn as much for large values of input, is what I can see. Both. Of course, the final activation function is a weighted sum of these two terms, which will look
Correct.
more like the blue or more like the orange, depending on the problem.
Yeah, it's very interesting actually that they came up with that idea from the Cauchy integral. It's pretty cool.
Actually, I have tried cans also. Cans, I found it pretty difficult to train, especially even a problem like MNIST. First paper of can I tried to duplicate, and I didn't have a good experience trying to duplicate it for MNIST. By the way, the original can paper didn't talk about MNIST problem. They only talk about some simple function approximations. But I tried to apply it to can, so MNIST problem. And MNIST itself, MNIST is supposedly a trivial problem. Today, 2025, Jan Lekan rose to fame by solving that problem.
Correct.
But today it is a trivial problem. But I had a difficult time, especially with the B-splines, figuring out how many points you need and what should be the order, and there were like too many parameters there to tweak that. Here it's just 3 parameters, so that part I really like that.
B-splines are and Chebyshevs are all complex. Poles, knots, this, that, whatnot, basis functions. Yes, they are pretty complex.
Yeah, but I've heard the Chebby can and the Wave can, they claim it is better, or say, what do you say?
Oh, is it? Okay.
Them. Apparently, it's easier to train them compared to B-splines.
Interesting.
So compared to B-splines, Chebby can and Wave can, you can see those two papers. They claim to have much easier training. But what is interesting is the paper, the XNet versus CAN paper, it says it outperforms all of them. So that's interesting.
Nice. Are you using this today in some actual?
Yes. So I am also training some models for my own company as well as other companies, and I am actively using this actually. heavily
Nice.
using this,
Mm.
and it has definitely made a significant difference.
Nice.
For one thing, I can tell you, for people who don't have a lot of money, like to buy like a lot of GPUs, which is definitely the case with me, and I assume a vast majority of people fall in the similar category. It makes a huge difference when you speed up the training.
Yeah.
Just as a fun, no, like I did my machine. I was training some model for like 3-4 days, and then what happened is it heated a lot, and then the GPU started really literally crying, and then I had to basically disassemble the system. Also there were problems with the fan and stuff. I had to like yeah. So
Mm.
and it also, right, it starts slowing down once your
Mm.
GPU gets heated up, right? Your GPU performance actually goes down. It starts to throttle itself and then to bring down the temperature. So
Right. It
that's
does
not
to
fine.
regular CPUs too. I mean, anytime
Unless you have like liquid cooling and all,
liquid cooling, yes.
which could probably avoid it.
Mm-hmm. Agreed. Yeah.
Yeah,
Interesting.
or you could have air condition, then it's fine.
Well, in winter weather, you can just keep it outside.
Question.
Yes, Badri.
Does it make sense, for example, if you send the same MNIST data set to a Khan model, which you said you did, and then the Khan model is supposed to give out the activation function that it learned from the data set. And given that the Cauchy activation function is the most accurate, has the highest accuracy for this data set, the Khan model's output activation function should be as close to Cauchy as possible. Or does it make sense to compare what it outputs? And
No,
compare it
there
to
you
Cauchy?
cannot exactly compare and expect the same result, because here you have the matrix also involved there. So there is a linear transforms in between. In CAN, there is no linear transform. So it's completely only activation function and just adding all the activation function outputs. Completely they got rid of linear transform. So I don't think you can, it's not easy, straightforward to just compare and then say.
But tell me one thing. Okay, now this is an interesting thing that you mentioned. No linear transform, no matrices. So what does it mean in terms of the pricing? Khans are using less GPU then?
Khans are using no matrices, so only additions. But then for learning those parameters of the learnable functions, right? That's a lot of parameters actually in CAN. So those will need involve quite a bit of computation there also. So
okay, the question was that essentially, is it cheaper to run a Khan model than a MLP actually? Because there are no transformer model, because there are no.
I think the answer to that depends on your hardware. So let's say I have a hardware that has only addition blocks. It doesn't have matrix multiplication blocks, and maybe in those hardware the CAN will run may run faster. And the functions you can have as memory, right? Once you learn the functions, they can be just lookup tables. So with just lookup tables and addition operations, CAN can be implemented.
Correct.
Whereas MLP, you will need matrix multiplications, which are pretty expensive. But if you have a GPU that, GPUs are designed, in fact, to do the matrix multiplications very efficiently. So I think in the GPU case, I don't see a major advantage of CANs. But when the CAN originally came, their claim was, if I recall, their claim was total number of neurons are lesser. So for the same problem, you can solve with fewer neurons is because each neuron is now more expressive. That was the claim. Whether it really happened is a different thing. I think.
Also, I think interpretability. They talk about the fact that you can interpret it as
that is
standard
another
functions.
benefit. Yes. A good point actually. Interpretability was also one of the important benefits they claim of CANs. Yeah. MLPs, we don't yet have that level of interpretability.
So again, going back, for every neuron, you have essentially trained weights, biases, and the Cauchy function.
Yes.
So the 3 parameters essentially.
Yes, correct. 3 parameters.
Yes. Is it okay? So the more parameters you add to learn, isn't that kind of it can may not find the solution quickly? So again, my question is, in certain cases, do you need more data actually? The amount of data you need to learn, because
that has to follow the scaling laws. There is a general scaling law that to train a model, I mean, again, this is just a rule of thumb, okay? So don't come after me for it. So the rule of thumb, what I've heard is, if there are X number of parameters in your model, you need 10 times X, that much amount of data points. So if you're talking about training a 1 million size model, 1 million parameter model, you need to have 10 million data points.
So you just essentially said that with Cauchy, you're going to have 30x more.
Yeah, it depends how much parameters you added more in the Cauchy case.
Correct.
This is where I think it's you have a room to play there, right? Like whether every neuron you want to have a different activation function, or I want to share the same activation function across in one layer, right? Layer to layer I can have different, or you can even have one activation function for the whole network, right? All neurons. So these are all some things you can play with and see which does better.
Interesting. Good point. Yeah.
So maybe this is a programming question. So that level of control, can we have that at the Python level? In other words, combining specifying the activation function at each neuron level is very simple, right? I mean, it's just implicit. But how do you partition the neurons or layers? Is that control we have at the PyTorch level?
Yeah, definitely in the model, right? When we are defining the model, you'll have to decide okay, I did it in one way, but if you want, let's say this itself is a configurable parameter, right? You could write code that way. Like, do you want it to be per neuron configurable, or do you want it to be per layer, or you want it to be one for the whole network? It's possible to write a code like that.
Okay. I know it's possible. I was checking whether it's already there or not. Yeah.
PyTorch is pretty, I think it's pretty easy actually, PyTorch. Okay. Only thing what I have found in PyTorch, is that you have to be very careful with the dimensions. So you have to know, like when you're handling multi-dimensions, especially when you have to be careful with the dimensions. And then there's this broadcasting thing that happens, phenomenon that happens in PyTorch. You have to be very careful what you're doing there. So as long as you watch you have a good understanding of broadcasting, and then you have a good understanding of multi-dimensional arrays, handling them, because sometimes you'll have to reshape, like you make something 3 by 2 by 5 as 2 by 3 by 5, right? So you reshape So when you do those kind of things, you have to be careful. So that's what my experience has been. But otherwise, PyTorch is pretty easy. You know, many things can be very easily done.
Hey, so Sundar, can people here access this code that you have there in Lightning? I'd love to play with it actually to understand.
Yeah, I'm happy to share to discuss how to exactly to do that.
So Shinda, it will be in the course portal. The same. Remember, if you are all part of the weekly paper reading seminar, then you'll see a topic called XNet, and under that topic, we'll host the Jupyter notebook. And I'll send a link to it.
Is it a collab, right? No, is it a collab or a Jupyter?
It's a Jupyter notebook.
It's a Jupyter notebook. You can run it wherever you want, Collab or Lightning. I ran it on lightning.ai. For Collab also you can run. You can run locally in your machine also you can run. So people who don't have a GPU and you just want to play with things before deciding to buy a GPU, I would recommend lightning.ai. Temporarily try it out, get comfortable, then go and pay 10 Huang.
Everybody is paying Jensen Huang, yeah.
He claims that is the best investment for the decade.
Yes, yes. Great session, Sundar. Loved it.
Thank you. Yeah. Hope to do more like this.